Good afternoon. My name is Doug Schmidt. I'm here to talk to you about Shipboard Advanced Metal Manufacturing. We are just getting started on this project as a Phase 2. We have the objective to develop a shipboard advanced metal manufacturing capability for the Navy to service on-demand parts. We are Boston Engineering, a company with about 65 people in Waltham, Massachusetts, comprised of electrical, mechanical, and software engineers. We handle everything from devices, UAVs, and robots to thermal spray systems. We maintain certain certifications, including ISO 13485 and ISO 9001. We've been in service for over 30 years. Boston Engineering maintains centers of excellence, including digital solutions, robotics, control systems, embedded systems, and design for any solution, which can include any assembly, cost, serviceability, and modularity, among others. We service the medical, commercial, and government entities. On the government side, we are focused on the Afloat program. Other Phase 2s include above-water robotics, with past efforts including biofouling and thermal spray robots to lay down new decking on carriers. For this program, our objective is to develop a complete shipboard system for the additive and subtractive manufacturing that can compete with current logistics applications and the need to supply sailors far away from home. The ultimate goal is the determination of the part as seaworthy as it is manufactured and delivering that part to the warfighter. This ultimately means defining the capabilities to withstand the motion of the ship on the ocean, as well as shock and vibrations, maintaining quality parts and components. The Navy is the first customer. We expect them to use just-in-time components delivered by the laser-directed energy deposition to reduce the logistics and supply demand. Commercial shipping, where your home base is well behind you, can also use the technology of components on demand, much the same way as the Navy, where the supply is not readily available and demand can drive the cost skyward in remote locations. The next commercial area would be placement in remote locations where supply is not readily available. Supplies can be carried into the site in wire and equipment and turned into the component needed, at the site needed, regardless of the contestation. Remote locations, where long lead times and material usage are critical, can be very important to service parts. The last step is the forming of molds for other high-volume components. These molds can be made in any shape desired and constructed continuously. Finally, changes to the mold are cheap. New features can be easily added for high-volume manufacturing. From the naval standpoint, additive manufacturing would reduce the Navy requirements, requiring logistics and shipboard procurement. It could provide difficult-to-source parts by developing the unique tools on board. With wire, combined with laser-directed energy deposition system, the part is already on board the ship. Reliance on supply chain logistics and service can be reduced. As an example, if a U.S. Navy supply ship carries 250 tons of general cargo, much of that comprises shipboard supplies, as a portion of the supplies needs procurement or stocking. A greater fuel or weapons capability might be possible with the reduction in supplies. The laser-directed energy deposition system can assist in providing significant portions of those parts, allowing the sailor to experience a ship that is fully active. While the upside is great, there are some challenges. Specific limitations include most systems being currently designed for laboratory or land-based machine spaces. Boston Engineering is interested in bringing this on to the naval shipboard, mitigating the severe degradation, allowing the performance that can withstand those pressures. Two land-based systems exist: the powder bed fusion and the wire arc additive manufacturing. Each of these systems has its advantages. Powder bed fusion details the most intricate parts on the order features of 50 to 100 micrometers, although the overall size is small and powder handling can cause issues. It deals with sub-micron metal powders, dangerous to shipboard processes, as metal powders can explode. Wire arc additive manufacturing has a greater deposition rate with wire but lacks the precision necessary for details. The laser-directed energy deposition provides a wire-based system with the near-net shaped part-making capability. It proves a good middle ground between the two manufacturing methods. With a 6-axis robotic holder and a 2-axis part holder, parts are accessible, with total sizes on the order of multiple feet. This provides the maximum net shape components with only minimal machining. This is especially important as machine shops, in general, do not have the height nor width to add additional equipment. Additional equipment must be compact and robust. This is the case with this robotic design. This would free the warfighter to perform tasks, not beholden to machines or parts not working. No more waiting on a part or component. One of the larger challenges is the land-based focus of these machines. Focusing on the shock and vibe and adding the challenging part of the subtractive component is the current focus of the effort. Boston Engineering is just beginning transition to the fleet in 2028 with a single deployment to a ship in this early stage Phase 2 process. Deploying to a ship includes the geometry of the additive and subtractive components, with modifications to allow for differing shipboard structures. Boston Engineering would need shipboard qualification of the actual shock and vibe, either by FEA analysis of the entire system or using the accessing a vibration table for various components. In the end, we would like to see first article controls and sensors for the system, along with sailor training, to develop the methodology for construction of a components. Moving beyond the Phase 2 capability, Boston Engineering would hope to develop digital twins to adjust for the active shock and vibration mounting, as well as reveal defects and provide additional process speed. All this should bring the warfighter up to their full capabilities, with all systems go. We expect the market to continue to grow for additive manufacturing, achieving about $100 to $200 million in the next 5 years. We have a system that is wire-fed without the dangerous powders, providing near net-shape capability. The unique wire-conforming capability, with the variety of materials which include both stainless steel as well as copper, nickel, and titanium, provide a unique set of qualifiers for naval deployment. The challenges reside in reaching the TRL 7 to 9 category, to which this SBIR is devoted. This will provide manufacturing on ships, with the unique capability to define parts at the component level when it is needed most. We are looking for primes to spearhead the ship project for the Navy Afloat program in metal-added capacity. Focusing under subsequent Phase 2 or Phase 3s, we have a vested interest in naval criterion and how that applies to the laser-directed energy deposition manufacturing. Specific interest includes shipboard robots and the unique tools for subtractive removal, as well as understanding of elimination of the shock and vibration experienced. With the myriads of configurations aboard any vessel, it is imperative that we understand each vessel and the scope that goes with it. Our specification includes modification of size and configuration. With it, we can hope to satisfy new vessels and bring the additive and subtractive manufacturing to the Navy in 2028. If you are looking for more information from this presentation, please call me. My contact information is listed on this slide. We look forward to seeing you.